Hi everybody. We are solving dynamics problems. Our topic is force, mass, and acceleration. We are solving kinetics problems. We are solving problems by directly applying Newton's second law. Now we have the following question. A collar with mass m slides on a vertical shaft under the influence of a force F whose magnitude is constant but whose direction is variable. Theta equals kt, where k is a constant. Find the magnitude of the force F that will stop the collar when theta equals pi over 2 radians, which starts moving from rest when theta equals 0. The coefficient of kinetic friction between the collar and the shaft is mu k. Yes, there is a force whose magnitude is constant but whose direction is variable. It is applied to the collar. It starts being applied when theta equals 0. Then the angle theta is gradually increased, and the force F is made horizontal. Theta becomes pi over 2 radians. It becomes 90 degrees. There is friction. The coefficient of friction is mu k. The kinetic friction coefficient is mu k. What should the magnitude of this force be? We are asked to find it in terms of the given information. Theta changes with time according to the relation theta equals kt, and k is constant. It is resting initially. It comes to rest in the second position. It is resting at the beginning. Then it comes to rest again when theta equals pi over 2 radians. Now we will find the force F. Let's find it. What kind of motion is this? Rectilinear motion in the vertical direction. Its trajectory is linear. We are examining the motion of a collar. It performs rectilinear motion in the vertical direction. Its velocity is variable. It starts from rest, accelerates, then slows down and stops again. Its acceleration is also variable. It first accelerates, then changes direction and slows down. We will examine this motion between two positions. In the first position, theta equals 0 and the velocity equals 0. In the second position, theta equals pi over 2 radians. The velocity is again 0. It moves upwards starting from below. It stops initially, then stops again in the second position. There is acceleration first, then deceleration. Let's draw the free body diagram. Let's first draw the free body diagram in the first position. There's the gravitational force and the force F. There's no force applied by the shaft because the shaft doesn't need to apply a force. The velocity is 0 yet. There's no motion. Therefore, there's no slippage. Consequently, friction force hasn't yet been created. There's also no normal force because it doesn't need to be created. In the second position, there's a normal force, but again, there's no friction force because it's stationary. There's no slippage, no motion. Therefore, there's an uncertainty there. It slipped and slipped, then stopped. It will return. We don't consider that uncertainty. Whether we show the friction force or not, it doesn't change anything anyway. Now let's consider an intermediate position. Let's draw the free body diagram in the intermediate position. Let's show the forces. We're applying the force F. There is the gravitational force, and the force applied by the shaft has two perpendicular components. The force applied by the shaft to the collar has a normal component and a friction component. We represent the normal force horizontally, perpendicular to the shaft axis, to the left. The figure shows that this force should be to the left because the component of force F perpendicular to the shaft axis is to the right. Force F is on the right side. The friction force is in the direction of preventing slippage. The collar is sliding upwards. Therefore, the friction force is downwards. Let's represent the acceleration. We said acceleration is variable. Initially, it accelerates. Then, after a certain point, it starts to decelerate. Because the collar first stops, it needs to accelerate. Then, to stop, it needs to decelerate. There is an acceleration that causes first acceleration and then deceleration. At a certain point, the velocity is maximum. At that certain moment, the acceleration changes direction. The acceleration becomes zero. Now let's write Newton's second law in the direction parallel to the shaft axis. Let's align that direction with the y-axis. Let's define the upward side as the positive side. Let's choose it. Total Fy equals may. The sum of the projections of the forces onto the y-axis is equal to may. There are 3 forces projected onto the y-axis. The normal force is perpendicular to the y-axis. The projection of the force F is F cosine theta. It is upward, therefore positive. The friction force is downward, therefore negative. Its projection is equal to itself, minus mu kn. The projection of the gravitational force is also equal to itself. It is downward, therefore negative. Minus W equals may. Ay is equal to A itself, because A is parallel to the y-axis. The sign resulting from the direction is inside A. We don't write anything plus or minus in front of it. Now we will find the force F from this. But first we need to find out what the normal force is, in terms of the given values. Let's write Newton's second law on the x-axis. Total Fx equals max. Since the acceleration is perpendicular to the x-axis, its projection is 0. That is, the right side, the opposite side, is 0. The sum of the forces is equal to 0. When we set the sum of the forces equal to 0, we see that n equals F sinus theta. We see that the normal force is equal to F sinus theta. This is because the friction force and the gravitational force do not have a projection onto the x-axis. The normal force does have a projection. The force F has a projection. These are equal to each other. They are in opposite directions. So, n equals F sinus theta. In this equation, we can write F sinus theta instead of n and dv over dt instead of A. Since the motion is rectilinear motion, we know that the magnitude of the acceleration is equal to the derivative of the velocity with respect to time. The relationship A equals dv over dt can be used. We can write dv over dt instead of A. Now, since the variable on the left side is theta, we need to find the value of dt on the right side in terms of d theta. Let's find it. Starting from the relation theta equals kt, by taking the differential of both sides, we obtain a relationship between dt and d theta. We see that dt equals d theta over k. We write d theta over k instead of dt. We move d theta to the left side. We rearrange. We take the integral of both sides. We also know that the weight force is mg. We write mg instead of w. The magnitude of F is stated to be constant. Therefore, we can take it out of the integral. What remains inside? Cosine theta minus mu k sinus theta. We write d theta next to it. We write mg instead of w, integral d theta. On the other side, k and m are constants. Let's leave them outside the integral. Integral dv. Now let's define the limits. We will take these integrals between the first and second positions. The first position is the lower limit value. The second position is the upper limit value. At the lower limit, theta equals 0 and v equals 0. Both are 0. At the second position, that is, at the upper limit of the integral, theta equals pi over 2 radians. And v is 0. Again 0. So what does this mean? The other side is 0. When we integrate from 0 to 0, the integral of dv is 0. The other side is 0. If we integrate on the left side and perform the necessary operations, we find F. We find F equals pi mg over 2 multiplied by 1 minus mu k. If we examine this relationship a little more closely, what does it change whether the coefficient of friction is large or small? Let's see. If there is no friction, for example, if mu k equals 0, then we get F equals pi mg over 2. The expression inside the parentheses becomes 1. But if friction increases, the expression inside the parentheses decreases. When the expression inside the parentheses decreases, F increases. Does that make sense? Yes, it does. So that's it. Goodbye.